as the degree of its neighbors. So degree of a vertex V is a measure of it. Eigenvector centrality for vertex V is a measure of its degree along with the degree of its neighbors. So now let us consider 0 and 3. So 0 has 3 neighbors, vertex 3 also has 3 neighbors. But if you look at the eigenvector centrality for these, 0 is 0.489, for vertex 3 is 0.467. There's a slight difference between the two. Whereas vertex 2 has the same value as 0. Because vertices 0 and 2 have identical neighbors, in the sense that 0 has 1, 2 and 3 as neighbors. 2 also has 0, 1, 3 as neighbors. So there's no way they're different from each other. Whereas 0 and 3, you see here 0 has, of course, 1, 2 and 3 as neighbors, 3 neighbors. Then 3 has 0, 2 and 4 as neighbors. Now 0 has this neighbor 1, which has 2 neighbors that have a high degree, whereas this vertex 3 has this neighbor 4 that has a degree of 2, as well as it has neighbors that have like 3 and 5 that have a lower eigenvector centrality. Okay, let us pick a more better example. Let us pick 1 and 5 for that matter. 1 has a degree of 2, okay, and 5 has a degree of 3. So you may think the eigenvector centrality of 5 should be larger than the eigenvector centrality of 1, because 5 has a larger degree than vertex 1. But look at the neighbors of 5 and the neighbors of 1. The neighbors of 5 have what? They all have degree 2. Whereas the neighbors of 1, they have degree 3. So eigenvector centrality is not just based on the degree of a vertex, it's also based on the degree of its neighbors. Everything considered together. So that is why the eigenvector centrality of 1 is actually larger, 0.364, than the eigenvector centrality of 5. See the number here? Because even though 1 has a smaller degree than 5, you take into account the degree of the neighbors of 1. The neighbors of 1 are 0 and 2. They have a larger degree. Whereas the neighbors of 5, 4, 6 and 7, they have a smaller degree. So this measure considers everything together and quantifies the importance of a vertex. So it's not just the degree of the vertex, it's also the degree of the neighbors that's taken into consideration. So everything taken together and one single value to quantify the whole thing. So again, as I said in the first class, we're trying to quantify the importance with this as just one number like this. Okay, so eigenvector centrality will range from 0 to 1, and larger the value, the more important the vertex is. So in this graph, 0 and 2 have the largest eigenvector centrality values. So they are the most important from the eigenvector centrality point of view. And as I said, you not only take the degree of a vertex into consideration, you also take the degree of its neighbors into consideration and quantify the importance of a vertex. So let us go through the calculations for eigenvector centrality. So you go through a sequence of iterations. So the first iteration is same as computing the degree of centrality. So you take the adjacency matrix and multiply it by a column vector of all ones, and you get the degree centrality. So now what you do after you get the product column vector is you normalize the entries in the product column vector. So how would you normalize the entries? So this is one way of normalization of a set of data. You will see that repeated in this course. So you square these numbers. It's like 3 square plus 2 square, okay? 3 square plus 2 square plus 3 square plus 3 square. So square all these numbers, sum them up, okay? And take a square root of that sum. So it's a square root of 3 square plus 2 square plus 3 square and all these values. So let us say that comes out to be some n. Okay, sum of the square root of the sum of the squares. And then what you do is you divide each of these entries by that n. Okay, and that is these numbers. Is that clear how we get that? So sum of the square root of the sum of the squares of these numbers, and whatever the square root value is, divide each entry here by that square root value, and that's these numbers. So it's always going to be from 0 to 1. So that's what is called normalization. Okay? Is that clear? How to do normalization?
Over it again.
One more time.
So once you square root the squares of each, then you sum them up and then you divide the original value by the sum?
Original is 3.
Correct, by the sum, the squared sum.
Yeah, so if you want to, yeah.
I just missed that last step.
Yes, good. So how many 3's are there? 4 3's, right? So it's 3 squared times 4 plus how many 2's? 4 2's. So it's going to be like what? 3 square is 9 times 4 plus 4 times 4. So that's like 36 plus 16. 52. Right? So the sum of the squares is 52. Then take a square root of that. So square root of 52 is roughly around 7.3, let us say. So divide each entry by 7.3. So 3 divided by 7.3 is this 0.416. Then 2 divided by 7.3 is that 0.277 and so on. Okay? So again you have a 3, so 3 divided by 7.3, the same 3 is 0.416. Is that clear? That's how we normalize.
So we should have same value.
Yeah, so if you have the same values for the entries here, we're going to get the same values here also. The only thing is you're making them into fall in the range of 0 to 1. Okay? So now, that's the first iteration. Well, actually you have 7.21, that's the normalized value. Okay, so I have to put it here. So it's not 7.3, it's 7.21. Is that clear? So that's the square root of this. So this is the square root of the sum of the squares. Alright, so now repeat the process for each iteration. So the second iteration, okay, of course in each iteration use the adjacency matrix as a basis, and instead of multiplying by column vector of all ones, you multiply the adjacency matrix by this column vector, the normalized values. So 0.416, 0.277 and so on. So multiply the adjacency matrix with this column vector. And again, the same multiplication. How do you multiply now? So now the first case, the first iteration, you took into consideration the degree of the vertex, right? So in multiplying this row with this column vector, you took into consideration just the degree of the vertex. In the second iteration and all the subsequent iterations, by multiplying this row vector with this column vector like this, you capture the degrees of the neighbors of the vertex. Okay, so again, how we multiply? There's the same term by term multiplication. 0 times 0.416 plus 1 times 0.277 plus 1 times 0.416 plus 1 times 0.416 plus 0 times this term and so on. Okay. So sum all those entries, you will get 1.109. Is that clear? So when you sum, when you do 1 times this, times 1 times this, plus 1 times this. So it is only these three that will be non-zero. The others still will go to 0, right? So sum of these numbers is 1.109. Just matrix multiplication. So do that and get this product column vector. So again, now try to normalize this. So like we got this and normalized this, right? So try to find the normalized value. So how to get the normalized value now? It is the squares 1.109 square plus 0.832 square plus 1.109 square and so on. Then sum all those squares, take the square root of that sum, that is like 2.59. Okay? Then divide each entry by 2.59. So 1.109 divided by 2.59 is going to be 0.428. 0.832 by 2.59 is 0.321 and so on. So you start seeing the entries kind of start converging. Of course, we started with 1 and then ended up with this. Now the entries that we ended up in the first iteration, which are these, are kind of getting closer. So 0.416 and 0.428, 0.277 and 0.321. So they're trying to get closer. Right, so that is what you want to target. You want to continue the iterations until the entries get closer to each other. So we could go through several iterations like that until the values converge to a certain level of precision. Okay, so that is the standard approach. But for the course exam purposes, you don't want to try several such iterations. So the program I gave you actually runs like that until the values converge for each entry here in the column vector. But the way we'll do for the exam purposes, when you do it manually, the iterations, we will continue the iterations until this normalized value converges. So the normalized value at the end of the first iteration was 7.21. At the end of the second iteration is 2.59, farther away from each other. So we'll continue the iterations until the normalized value converges. So let us see the third iteration and see what happens. So the third iteration again used adjacent symmetries multiplied by the normalized column vector at the end of the second iteration. So again do the matrix multiplication. The multiply this row with this column vector to get this 1.177. And once you get the column vector, find its normalized value. So square these entries, sum of the squares, and take a square root of the sum of the squares. So that comes out to be 2.67. So you see now it was 2.59 in the previous iteration, it is now 2.67. So again divide each entry by 2.67 to get the normalized column vector. So continue the iterations like that. So the fourth iteration, you will multiply the adjacent symmetrics with this normalized column vector to get this one, and normalize the entries here, we get 2.64. So that's reasonably converged, 2.67 and 2.64. So if you go through few more iterations, after 7 iterations, you could get like even more convergence. So in exam purposes, I could tell use like 1 decimal convergence or 2 decimal convergence. So if I say 1 decimal convergence, you can actually stop here because 2.6 that's the first decimal and 2.6 is the first decimal. So you can stop there. So whatever is this normalized column vector at the end of that iteration, that is your eigenvector centrality. So if you stop after 4 iterations, the end column vector after normalization is your eigenvector, is the principal eigenvector, and the entries correspond to the eigenvector centrality. So if you've gone through 7 iterations with this approach, these will be the entries in the column vector, and the corresponding vertices are quantified based on that. So the first entry is for vertex 0, the second entry is for vertex 1, the third entry is for vertex 2, and so on. So vertex 0 has the So like here you have 0.479, but if you go through 7 iterations, you get 0.489 for vertex 0. You get 0.349 for vertex 1 after 4 iterations. If you go through 7 iterations, you get 0.364. Okay, so these entries quantify the topological importance of the vertex with respect to eigenvector centrality. That is the degree of the vertex along with the degree of its neighbors. Okay, so how the degree of the neighbors are taken into consideration? The subsequent iterations. The first iteration is just based on the degree. The subsequent iterations only multiply the same row vector with the column vector that has started taking into consideration the degree of the vertex along with its neighbors. You capture that. Okay, so if you go through several iterations until things get saturated or no longer changes, that's when you say you can stop. Okay. Any questions? So here, unlike degree centrality, there is chance of less ties. So unless the vertices are very similar to each other, like 0 and 2, they have the same neighbors. Okay, so that's why the eigenvector centralities are same. Whereas you can differentiate vertices even with a fraction of the decimal. So like 0 and 2, like I said before, it is very difficult to differentiate them because they have the same neighbors 1 and 3. But you see here, 3 has this 4 that has a lower degree as well as a lower eigenvector centrality. So all this is taken into consideration. So that's why you see a small difference between 0 and 3. 0 has 0.489, whereas vertex 3 has 0.467 as eigenvector centrality. So they are different from each other because of this vertex 4. Okay, and that is taken into consideration. Okay. Any question on this eigenvector centrality? I have some more examples that you can practice. So it's all computed for undirected graphs, which means there's no direction for the edges. Okay. So same thing. So given a graph, you should be able to write its adjacency matrix and go through the iterations. So the first iteration is like computing the degree centrality, multiply the adjacency matrix with the column vector of all ones, and you get the product column vector, and you need to normalize. So again, how do you normalize? Square these entries, then sum all of them, sum these entries, the squares, and take a square root. So that's going to be 4.69. Is that clear? So sum of these squares, and take a square root of that sum, and then divide each entry by the normalized value. So 1 divided by 4.69 is 0.213, 2 divided by 4.69 is 0.426, and so on. Second iteration, use the adjacency matrix, multiply the adjacency matrix by the column vector at the end of the first iteration. And again do the multiplication, now normalize these entries. Square them up, sum those squares, and take the square root of that sum, you get 2.19. Then divide each entry by 2.19. So repeat this process until the normalized value converges, which will take some iterations. So after 4 iterations, you actually get 2.21 and 2.21 in the third and fourth iteration for the normalized value. So these are the eigenvector centralities for the 5 vertices. So again, if you look at the numbers, vertex 4 has the largest eigenvector centrality of 0.616. So because it has largest degree as well as is connected to vertices 3 and 5 that has also larger degree relatively compared to the 1 and larger eigenvector centrality. So when you take the degree of the neighbors into consideration, it's actually the eigenvector centrality also taken into consideration. So all these things make vertex 4 to have a really large eigenvector centrality. Whereas vertex 2, so you may think vertex 2, let us compare vertex 2 and vertex 3. Vertex 2 has 0.352 and vertex 3 has 0.484. So you see here, even though vertex 2 and 3 both have degree 2, but the eigenvector centrality of vertex 2 is smaller than the eigenvector centrality of vertex 3. The reason is what? Can anyone explain the reason why vertex 2 has a smaller eigenvector centrality compared to 3?
So how do we like to?
Because
Huh?
the neighbors have more.
The neighbors have a larger eigenvector centrality. So 1 is a neighbor of 2 and 1 has a low degree, and it also because of that has a low eigenvector centrality. So the neighbors of 2 are 1 and 4. So even though 4 is there, 4 is also a neighbor of 3, whereas 3 has the other neighbor 5. So 5 has a larger degree, right? So it's not just yourself, it's based on your neighbors. Okay? So those are the reasons why vertex 2 has a lower eigenvector centrality compared to vertex 3. Is that clear? Okay?
So are you gonna tell us how many times to have to repeat the process?
Yeah, so I told you already. So what is when you stop, when the normalized value converges. So here the normalized value, the third iteration is 2.21 and the fourth iteration is also 2.21. But for exam purposes, I may also, because some graphs may take 10 iterations to even converge on this basis. So I may say go through 4 iterations. So after 4 iterations, you could stop. Yes?
Why don't we use the last values from iteration 4?
Why don't you are? That's what we say. Oh. Yeah, we. No, this, I think I didn't normalize this further. I normalized it, but I didn't divide this by 2.21. If you divide this by 2.21, it will be almost the same.
Would we, if it's almost the same but not the same, then which one do we use?
Use the last
Right,
latest
okay,
iteration.
just making sure we use the last
Yeah,
one.
yeah, latest iteration. Yes, you're right. So since the value came out to be the same, I just pick up this number. So yes, you're right. So when you divide this by 2.21, there will be some small differences. Because if you compare this with this, they are not exactly the same. So there might be some small differences.
Just making sure.
Okay, good. Okay, so I have one more example you can practice. So if you want to rank the vertices, you know what ranking means by now, right? So just look at the eigenvector centrality values. The larger the number, the higher the rank. Higher the rank means like your first rank means the topmost vertex. So 4 is the topmost rank because this corresponds to vertex 4. The vertices are labeled 1 through 6 in this graph. So the second rank is like this vertex, vertex 2. Then the third is 0.376, so vertex 1. Then you have vertices 5 and 6 are actually equally ranked. Then vertex 3 is the lowest eigenvector centrality. You can see from the graph it has a degree of 1 and it's connected to vertex 1, which also has a lower degree and relatively lower eigenvector centrality. So all these things make vertex 3 to have a lower eigenvector centrality. Okay? So later we'll see page rank, which is the algorithm used by Google and several other search algorithms to rank web pages. It's very similar to this. The edges are directed. Okay, the web graph is directed. That's one major difference there. But the idea is very similar. So it quantifies the importance of a vertex as well as the neighbors. And put together, you quantify the eigenvector centrality and also the page rank there. Okay, so let us now do the other one. So the first two that we saw are neighbor based or degree based. Now we are going to look at shortest path based centrality matrix. So closeness centrality is one such metric. So we already did most of this. Given a graph, we saw the first model how to get the distance matrix, right? So run the breadth first search algorithm to find the shortest path from each vertex to every other vertex, and thereby you can get the number of edges. So for vertex 1, it is connected to 2, 3, 4, 5 with just one edge, right, on the shortest path. So you have entries of 1. Whereas from vertex 1 to 6, the shortest path has 2 edges. 1, 2, then 2, 6. So the distance is 2 edges. Then 1 to 7 is 3 edges on the shortest path. So it is distance 3. Then 1 to 8 is 2 edges on the shortest path. So distance 2. So you get the distance from, or the number of edges on the shortest path from each vertex to every other vertex. So that is how you get the distance matrix. Is that clear how to get the distance matrix? Okay. So for vertex 2 you have 1, 6 and 8. So for vertex 2, 1, 6 and 8 have distance 1. Then to 7 you have distance 2. Then also to 3, 4 and 5. So you have distance 2. So that's the distance or number of edges on the shortest path from vertex 2. So now what we'll do is the closeness centrality of a vertex is basically the sum of all those distances right? So the sum of all those distances is 11. So like that you get the sum of the distances and just take the inverse of that. So 1 over 11, 1 over 11, 1 divided by 17. So the closeness centrality is the inverse of the sum of the distances for each vertex. Okay? So why? So when you just look at the sum of the distances, the smaller the sum of the distances, that's better, right? Because that means a vertex is closer to the other vertices overall. But throughout this module, we will maintain the convention. The larger the centrality value for the vertex, the higher the rank, or more important the vertex is. But with this basis, just the sum, it looks like what? Smaller the sum, the more important the vertex is, right? So to just reverse the trend, you take the inverse. So when you take the inverse, the smaller the sum, the larger the inverse. So it means the larger the centrality value, the more important the vertex is, right? So just to maintain that convention, because for degree and eigenvector centrality, that's what we follow. Larger the centrality value, the more important the vertex. So when you take the inverse or the sum of the distances, we maintain that. So larger the centrality value, the more important the vertex is. So you see here, vertex 7 has the sum of the distances as 21. So when you take the inverse of 21, it's going to be smaller than the inverse of 11. Right? So inverse has a property, isn't it? So 11 is less than 21, but the inverse of 11 is going to be greater than the inverse of 21. Okay? Clear? Alright. Now, one drawback with closeness centrality is it has the same weakness as degree centrality. The sum of the distances could be the same for two vertices. Like you see here, there are 2 11s here, and there are 4 17 here. So, which means if you rank based on closeness centrality, there could be some ties because you're dealing with integers. Okay? So that's why now we want to do something like eigenvector centrality, introduce the decimal numbers, okay, and capture the variation in the distance vectors. So if you look at the numbers here, especially in the case of say just the 2 11s, so even though the sum of the distances is 11, when you look at the entries here, this is the distance vector for vertex 1 and this is the distance vector for vertex 2. You see they don't have the same entries, isn't it? There's a difference. And now we want to also capture the variation in the distances. So if you look at the numbers here, the numbers are 1, 2 and 3 as the possible distances of vector for vertex 1. Whereas for vertex 2, the entries are like what? 1 and 2. There's no 3 actually here. Okay? So all the entries are either 1 or 2 for the distances. Whereas here the entries are mostly 1s, but there are some 2s as well as a 3. So we want to capture the variation in those distances. Okay? In the distance vector for each vertex. So to do that, we can use this spectral analysis thing that I gave you, the program. So this is one scenario where you would use the adjacency matrix. Like remember in the second module, like you use 6 programs, and two of them are like what? EVC underscore adjacency list. This is what I said you'll use mostly in the second module based on the adjacency list. Whereas there's one more thing called EVC underscore adjacency matrix. So far we use adjacency matrix of zeros and ones, or the Laplacian matrix, right? So the other matrix you would use is a distance matrix. So if you feed in the distance matrix to this program, it's going to give you the eigenvalues and eigenvectors. So here we use only the principal eigenvector. So this is the principal eigenvector based on the distance matrix. So if you look at the entries in the principal eigenvector, right, they capture, so they are going to be from 0 to 1, because always entries in the eigenvector are going to be from 0 to 1. So they capture not only the sum of the distances, or smaller values of the distances basically, it also captures the variation in those distances. So you see here, for vertices 1 and 2, even though the sum is the same, the entry that you have for vertices 1 and 2 in this principal eigenvector is different. Vertex 2 has 0.2518 if you go to 4 decimals precision, and vertex 1 has 0.2527. That small difference is because of this variation. Vertex 1 has more variation in its distance vector compared to vertex 2. So that is why vertex 2 has a larger, what's called closeness. So we call this as farness centrality. It's just a name that makes it look like far, but it's actually, it's like a variation of closeness centrality. Vertex 2 is actually more closer to the other vertices, and how closer it's also compared to vertex 1, because vertex 1 also has the same value for sum of distances. The variation in the distances is smaller for vertex 2 compared to vertex 1, because the entry here for vertex 2 is larger. Okay? Let us look at the 4 entries for 17. So 17 is this. So vertex 3, 4, 5, and 8. So if you look at the distance vector for them, vertex 3 has this entry, whereas vertex 8 has this entry. So which distance vector has more variation? The entry for vertex 3 is like 1, 2, 3, and 4. So it ranges from 1 to 4, the distance values. Whereas for 8, the distance values are 1, 2, or 3. There are more 3s out here. So there's what? More variation in vertex 3 compared to vertex 8. So even though the sum is 17, you see here vertex 8 has a lower value, 0.3763 compared to 0.3771 for vertex 3. So that means the smaller the value here, the smaller the variation. So vertex 8 is more closer to the other vertices compared to vertex 3. Is that clear? Because you cannot say based on this when you just compute the sum. But you see here there is one entry with 4 as the distance, whereas there's no entry with 4 as the distance. So if you go on that level of precision, vertex 8 is more closer to the other vertices compared to vertex 3. How that can be captured? By computing the principal eigenvector of the distance matrix. And if you go to this decimal precision, you see here vertex 8 has a smaller value compared to vertex 3. So we can say vertex 8 is more closer to the other vertices compared to vertex 3. Okay? Same thing with 2 and 1. So 2 has a smaller value compared to vertex 1. So vertex 2 is more closer to the other vertices compared to vertex 1. Okay? Any question? Whereas 3 and 4, they have identically the same distance vector. So, which means they should also have the same value for the principal eigenvector entries. Same as even 5. 5 also has the same. So all these 3 vertices have the same value. Okay, so there's no variation. So all are equally ranked. So you cannot distinguish them based on even the distances, the spread of the distances. Okay, they're clear. So that's the closeness centrality and this variation called far-ness centrality based on the principal eigenvector of the distance matrix. So now let us go through this betweenness centrality. So this is probably the most important centrality measure used in complex network analysis. So it captures the importance of a vertex for shortest path communication. So it is computed as this ratio and sum of these ratios. So if you want to compute the betweenness centrality of a particular vertex, what you do is you consider all pairs of vertices in the graph and find the number of shortest path between any two vertices. So that's the denominator, the number of shortest path between any two vertices like j and k, and how many of those shortest paths go through I. So for each such pair jk, find that fraction and sum all those fractions. Okay, so we'll see some examples. Okay, so let us consider this graph. And let us do for vertex 1. So we consider all pairs of vertices. So the pairs are like what? Anything other than vertex 1, 0, 2, 0, 3, and so on. 0, 4, 0, 5, 0, 6, 0, 7. Then of course 1 is the vertex we're looking at, so we cannot consider, so this is j and k. So the vertex we are looking at is vertex 1. So I is 1, then 2, 4, 2, 5, and so on. Now, I did not mention all the pairs here. Okay, we'll see the reason for that soon. But let's look at the pair 0, 5. So the pair 0, 5, how many shortest paths are there between 0 and 5 in this graph? One shortest path, right? What is that one shortest path? 0, 1, 5. So the ratio is there's total of one shortest path between 0 and 5, and that shortest path goes through the vertex 1. So it is 1 over 1. Okay? On the other hand, for the pair 0, 6, how many shortest paths are there for the pair 0, 6? Can I identify the shortest path for the pair 0, 6? One of them is 0, 2, 4, 6, 3 edges. That's the best we can do. What's the other one?
6, 5, 1,
6, 5, 1, 0 or 0, 1, 5, 6. So there are two shortest paths between 0 and 6, and one of the two shortest paths go through 1 because we're looking at vertex 1. So how many of those shortest paths between 0 and 6 go through 1? One of the two shortest paths go through vertex 1. So that's why it's 1 over 2. If both the shortest paths go through vertex 1, it is going to be 2 over 2. Okay? Let us look at the pair 2, 5. So between 2 and 5, how many shortest paths are there?
2.
2 and 5, two shortest paths. Let us see. There's one shortest path, which is this.
And
What's the other shortest path?
2, 1, 5.
2, 1, 5. Is there anything else?
2, 4.
2, 4, 5. Good. So there's one more.
Yeah, 2, 4.
So there are three shortest paths between 2 and 5. And how many of those three shortest paths go through our vertex 1? This path 2, 1, 5. So that's why the 3 shortest paths from 2 to 5 or between 2 and 5, and only one of them go through vertex 1. If 2 of them go through vertex 1, it will be 2 over 3. Okay? So you find such fractions and add up those fractions. Now the reason why I did not list all the pairs here, for the other pairs, they will have a shortest path between them, but they do not go through vertex 1. So for example, between 0 and 2, how many shortest paths are there between 0 and 2? It's just an edge between them, right? So it's a directed edge, just one edge. So there's one shortest path between 0 and 2, and that doesn't go through vertex 1. So it will be like 0 over 1, which is 0. For the pair, say 0, 3, how many shortest paths are there between 0 and 3? It's like this, right? 0, 2, 3. There's only one shortest path between 0 and 3. So again, there's one shortest path between 0 and 3, and none of them go through vertex 1. So it's 0 over 1. So that is why I did not include all the pairs. I include only those pairs that really go through vertex 1 and account for this betweenness centrality. So you add up all the fractions, that is the betweenness centrality of that vertex. Is that clear? So in the case of vertex 0, I say its betweenness centrality is 0 because none of the pairs go through vertex 0. 1 and 2, if they want to communicate, they can directly communicate. 1, 2 and 3, if they want to communicate, they can directly communicate. So if you look at all pairs like that, none of their shortest paths. So between 2 and 6, we have a shortest path that doesn't go through vertex 0. So no shortest path between any two vertices goes through vertex 0. So that is why its betweenness centrality is 0. So from betweenness point of view, vertex 0 is not important at all. No, none of the other vertices go through that vertex. Okay? So same way you can do for every vertex. For betweenness of vertex 2, consider all pairs of vertices and find how many of them go through vertex 2. So what's the fraction of the shortest paths between any two vertices go through that vertex. So that's sum all those fractions. You will get the betweenness centrality of that vertex. Is that clear? Okay. So based on that, these are the values of the betweenness centrality. So you find out that what? Vertex 5 has the largest betweenness centrality. Okay? And you see that it is a 0, 6 and 7 have betweenness centrality of 0. So even for vertex 6, none of the other vertices need to go through vertex 6 for shortest path communication. Same thing with 7. So those vertices have 0 betweenness centrality. So this is a more manual approach, means you have to consider all pairs of vertices explicitly and find the number of shortest paths between them and how many of them go through that vertex and so on, right? So it's more time consuming. So this is like a brute force approach. Okay? So we'll do more algorithmically. So here's another example to motivate this betweenness centrality. But we'll see a more algorithmic approach to compute betweenness now. So this is based on what is called breadth first search. So we saw this breadth first search in the first module. Remember? At that time I said we'll come back and use this to compute betweenness centrality. So let's go through this. So given a graph, so here the vertices are just labeled with alphabet A through G. So you can label either using numbers or alphabet like this. Alright, so we are going to just compute that fraction. One of those fractions that we saw there. Of course, we can compute all such fractions using this approach. So here we are computing the fraction, the betweenness centrality of, so looking at the pair AG. So AG is the vertex pair, and we are computing the betweenness centrality of the vertex C with respect to the pair AG. So like in the example before, we looked at like this, right? So we are looking at, say, the betweenness of vertex 1 with respect to the pair, say 2, 5. So the betweenness of vertex 1 with respect to the pair 2, 5 came out to be 1 over 3, right? So we are going to see how to compute these fractions, okay, using breadth first search. Okay, so there are two steps in this process. The first step is to actually run breadth first search and determine what is called the level numbers of the vertices. You know, when you run breadth first search, you get the level numbers, which is like the distance from the starting vertex or the root to the other vertices. So where to start breadth first search in this graph? So we are interested in the pair AG, right? So run breadth first search starting from A, and as well as run breadth first search starting from G. So let us run breadth first search starting from A. So A is said to be the root or the level, and its level is 0. So from A, you visit its neighbors. So its neighbors are B and D. So they are said to be at level 1. Okay? So these are the edges that you use to visit those neighbors. So now consider the vertices at level 1. So you have two vertices. So pick the lower alphabet. Okay? So B, its neighbors are D and F. Of course, D has been already visited, so we don't consider that. But F has not been visited, so A is being started and B and D are visited. So now F is visited. So the level of F is 1 more than the level of B because we're visiting F from D. So the level of F is 1 more than this. So 1 plus 1, 2. So now the other vertex at level 1 is D, but all its neighbors have been visited. So we don't consider vertex D. So now F is the vertex to be considered. It is at level 2. Visit its neighbors. So its neighbors are C and E. So the level numbers of C and E are 1 more than the level of F. So it is 2 plus 1, 3 and 2 plus 1, 3. Now there are two vertices at level 3, E and F. Just consider, so C and E. So pick up the lower alphabet, which is C. So visit its neighbors. So G is the only neighbor to be visited yet. So the level number of G is 4, 1 more than the level number of C. And E's neighbors already visited and so on. So that is how you get the level numbers of the vertices starting from A. So now do the same thing, find the level numbers of the vertices starting from G. So G is said to be at level 0, its two neighbors are at level 1. Then based on vertex C, F is at level 2. Then based on F, B and D are at level 3. Then based on B, A is at level 4. So these are the level numbers of the vertices. We did this several times in the first module also. Okay? So that's the first step. The second step is to use these level numbers as the basis to find the number of shortest paths from the root to the other vertices. So what is the root? The starting vertex. So these numbers indicate the number of shortest paths from the root, which is A, to the other vertices. These numbers indicate the number of shortest paths from G to the other vertices. So now let us see how to get those numbers. So for that, let me show one more slide that will actually capture the general principle. So let us say you have a root, some vertex here, and you have say 3 vertices U, V, W at some level, say I. Okay? So the dotted lines indicate the number of shortest paths. So you have 3 shortest paths from the root to U, you have 2 shortest paths from the root to V, and you have say 4 shortest paths from the root to W. Now let us pick a vertex X at level I plus 1. So 1 more than the level of these 3 vertices. Okay? Is that clear? So U, V and W are at some level I, and vertex X is at 1 more level larger than these vertices. So at level I plus 1. So the number of shortest paths from the root to this X is going to be what? Any idea? So X is connected to U, V and W, right? So you can reach X through all those shortest paths. So you can reach from the root to U, then take this edge to X. Or take this path from the root to U, then take the edge to X. then this shortest path from the root to u, then take h to x. So there are three shortest paths from the root to u, and based on this h to x, you can also say there are three shortest paths from root to x through u. Similarly, there are two shortest paths from the root to x through v. There are four shortest paths from the root to x through w. So the number of shortest paths from the root to x at level I plus 1 is what? Basically the sum of the number of shortest paths from the root to the vertices at the earlier level. Is that clear? So that's why I say here 3 plus 2 plus 4. So there are 9 shortest paths from root to x. Okay? Again, the shortest paths may have some overlap on the intermediate vertices. So you may have something like this from the root to some vertex, and then like this to u. Okay? So these are, say, the three shortest paths from the root to u. That's okay. Okay, still we can say there are three shortest paths from the root to x through u. You can go like this, then this, so that's one shortest path. Then, of course, I'll draw it a different color. And what is the other two shortest paths? So you can go like this to x, then this, x. So three shortest paths. Okay, even though there could be some overlap. Okay, so this is the basis to find the number of shortest paths from the root to a vertex. So how can we use that here? Let us start from the root itself. So we say the root to itself has one shortest path. Okay, so from A to itself you have one shortest path. So now go to the next larger level. So you know the number of shortest paths from A, from the root to vertices at level 0, which is itself. Now what about this vertex B at the next level, vertex 1? It's the sum of the number of shortest paths from the root to the vertices at the earlier level. What are the vertices at the earlier level? Just one vertex, right? So like in that case, if you just have one vertex, instead of like you say you have V, then W and so on. If you just had U, the number of shortest paths from the root to X is the same as the number of shortest paths from the root to U. If you don't have the other vertices V and W. The same thing here. For B, there's only one vertex at the earlier level. So the number of shortest paths from the root to B is same as the number of shortest paths from the root to that vertex at the earlier level. So which is A itself. So that's why you have a 1. Same thing for D. There's only one vertex at the earlier level. What about F? It is at level 2. There are two vertices at the earlier level, which are B and D. How many shortest paths are there? To B, which is 1, to D is also 1. So it is 1 plus 1, which is 2. There are two shortest paths from the root to F. What about C and E? C is at level 3. There's one vertex at the earlier level, which is F, right? So the number of shortest paths from the root to C is the same as the number of shortest paths from the root to F, because there's only one vertex at the earlier level. So it is going to be also 2. Similarly, the number of shortest paths from the root to E, which is at level 3, is going to be same as the number of shortest paths from the root to F, because there's only one vertex at the earlier level. So it is also 2. What about G? G is at level 4. It has how many vertices at the earlier level? 2 of them, C and E. So there are two shortest paths to C, there are two shortest paths to E. The sum is going to be 4. So there are 4 shortest paths from the root to G. Is that clear? That is how you get the number of shortest paths from the root to vertex at that particular level. Just sum the number of shortest paths from the root to the vertices at the earlier level, the previous level. So you do the same analysis on this. So it's called a breadth first search tree. If you put together all the edges that you used to visit the vertices. So starting from G, so the number of shortest paths from G to itself is 1. Now to C and E, C is at level 1. How many vertices are at the earlier level? Only one vertex. So it's the same number of shortest paths. Now for F at level 2, you have 2 vertices at the earlier level. So So we have to sum those distance, number of shortest paths, 1 and 1, which is 2. What about B and D? How many vertices they have the earlier level for each of them? Just F. B is at level 3, F is at level 2. So how many shortest paths from G to B? It's the same as the number of shortest paths from G to F. Okay, there's 2. Now for A is at level 4. How many vertices at the earlier level? 2 vertices. So how many shortest paths from G to B? 2 shortest paths. How many from G to D? 2 shortest paths. So sum those shortest paths is 4 shortest paths to A from G. So the final number that you got should match. So here from A to G you have 4 shortest paths. From G to A you also have 4 shortest paths. They should match, of course, right? So now what we're interested at? So we're interested at the betweenness centrality for vertex C based on the pair AG. Okay, so which means among the shortest paths between A and G, how many of them go through C? That's what you want to find. What's the fraction of the shortest paths between A and G that go through C? We'll find out that and we'll stop. Is that clear? So to get that fraction, we did all these things. Of course, first let me finish the fraction. So to find the fraction of the shortest paths between A and G that go through C, find first the number of shortest paths from A through C. The number of shortest paths from A to C is 2. What's the number of shortest paths from G to C? 1, right? So from A to C, you have 2 shortest paths. From G to C, you have 1 shortest path, right? So how many shortest paths are there from A to G that go through C? Huh? How many shortest paths from A to G go through C? 2. Why? Because this shortest path to C and then this path. You have to continue, right? So you take the road from this A to C like this and then continue on this path from C to G. So there's still one path. And this is the other path, A to C and then this path. So only 2 shortest paths. So in general, you may have a situation like this. You will have, say, from A, so you're looking at a pair AG and looking at some intermediate vertex C. If you have, say, some X number of shortest paths from A to C, in this case, say 3, and you have, say, some Y number of shortest paths from from G to C, just say 4. How many shortest paths are there from A to G that go through C, in this case?
12.
Huh?
12.
Multiply together.
3 multiplied by 4. Is that clear? Why? Because we can take each of these shortest paths. So let us take this path. Once I reach C, I can take now any of these 4 shortest paths to G. So it's already 4 shortest paths. Then I can try this shortest path to C, then I can take any of these 4. Similarly, I can take this path and go through any of these 4. So that's why it is the product. You see here, the product of the number of shortest paths from A to C and the product of the number of shortest paths from G to C. So you take the product of them, which is 2 in this case. So now you know from this that there are 4 shortest paths from A to G and 2 of them go through those to C, through C. So the fraction is 2 over 4. So that is how you get the fraction. Now you may think we did a lot of work to just get one fraction. Not really. We picked up the pair AG and found a fraction based on C. Now we can also do for all the vertices. So betweeness centrality for any vertex based on the pair AG, based on vertex B, based on like we did for C, based on the vertex D. So we can get all these fractions for based on the pair AG, right? And this level numbers is based on each vertex, A, G, and so on. So run breadth first search once from each vertex. right? So you'll get the level numbers. And based on the level numbers, you can get the distances. So all you have to do is run breadth first search for each vertex. That's what we have to do. So time complexity is going to be, we'll just, sorry, it takes one more minute. So the time complexity is going to be the time complexity of breadth first search, which is V plus E from graph theory. You have to run V on V edges, covering V vertices, covering E edges. So that is for running breadth first search once. How many times we have to run on each of these vertices? So that is the time complexity for betweeness centrality, V square plus VE. Okay. Now at the worst case, E could be V square. You could have V square edges connecting the vertices. Okay. So which means it is VQ because this is more dominating than this term. Okay. So we say VQ is the time complexity for betweeness centrality with this approach. Is that clear? So this is more computationally heavy compared to degree centrality. Right? There's one more example, we'll look at it next time. I encourage you to go and practice that example before you come.